Hi, welcome back again, everyone. You're watching a video lecture of solar forecasting, and this is a project based in Thailand. I'm Jigamut Songsiri. I have given previous lectures about the forecasting principle, important features in solar forecasting, and some overview of the forecasting techniques that rely on statistical methods like regression, like tree-based models in machine learning, and some of the neural network. Um, so, so I would like to dive into examples of numerical examples that has been our case studies for the previous 5 or 6 years, and so before that, I would like to give a lecture about how to evaluate the performance, and then give you a few samples of the case studies that particularly focus on the deterministic forecasting. Okay, let's get started. For the performance evaluation, let's try to make it clear about the concept of the loss function and evaluation metric. So when we use the term loss or objective function, um, most of the time we means the objective in the training process. It indicates in what sense is the model optimal. So the loss function is a penalty that manipulate your training process so that the model parameter is adapted so that the objective is at optimal. So the model parameter will have behavior or any characteristic that are governed by the loss function. You may have seen examples of the loss function in the regression problem. Typically, the most common one would be L1 norm, L2 norm, that is known as MAE, and 2 norm is known as MSE. But in fact, the 2 norm, which is the 2 norm of the error, is typically the square root, right? So to be exact, the L2 norm is the RMSE. But you can use 2 norm, but I mean, in the optimization process, you actually use MSE, which is the 2 norm square, so that the loss function is differentiable. Um, so when you consider different loss function, if you make a plot, example in this graph is obviously the 2 norm. The 2 norm, which is the blue line. This is the parabola curve, the square function. The 1 norm, which is the absolute, the 1 norm is the 1 norm of the error is the sum of absolute value when k from 1 to n. Okay. So if I make a plot, so I take a look at the loss function as a function of the residual or the function of error. Okay, so I plot it for the scalar case. Okay, the scalar case. So for the 1 norm, it would be just the absolute value function. So in robust regression, there is a common use of the Hilbert function, which is given by the orange curve. It basically parameterized by a cutoff that can be determined by the user. So when your error is small, when your error is smaller than the cutoff, the penalty is quadratic term. And when your error is larger than the cutoff value, the loss becomes the linear function. So so choosing an appropriate loss depends on your purpose of training the model. So if you want to penalize the residual error more in a very higher degree, you can pick the 2 norm or the MSE. But when your data sets have a lot of outliers, have a lot of outliers, and those outliers typically correspond to a very large residual. And if you want your model to be less sensitive to those large residuals that come from the outliers, you can pick something that is a robust loss, that is Huber function, or you can use the MAE. Because these two functions, you can see from the graph that when the residual is large, the penalty degree of the one norm and the Huber function is much less than the two norm loss, right? So when you penalize less, it means that you tend to care less about the large residual if those large residual are from the outliers. So that's a quick guideline. Okay. Um, and let me point it out that choosing the loss function are not trial and error. Okay. Um, they are not uh they are not they are not random, quantities. So as I said, you pick the one that fits best to your purpose of training. On the other hand, the evaluation metric is the quality index of your estimated model. So it's used in the validation and the test process. So you can, when the model is trained under a certain loss, you can still in the test or the evaluation or in the validation process, you can still evaluate your model using other metrics or all of them. You train with MAE, you can evaluate with MAE, RMSE, MBE, and all that. Okay. When your model is trained under a certain load, obviously your model will perform best when you evaluate with such metric. Okay, so you have, suppose you have suppose I have RMSE. I have MSE. So I have MSE. I have model A, I have model B. So the model A, if you control the model architecture, you have the model A that trained with MAE. You have the model B that is trained with MSE. When you evaluate to the two models, certainly you can evaluate the two model using the two metrics. But the model that is trained under MAE would have better MAE metric value than the model B that is trained under different laws. And similarly, the model B that is trained under MSE will have a better MSE value than the model A. That is typical because the model A is optimal in the MAE sense, so the evaluation metric should be better in MAE. Okay, that's a quick conclusion. Now let's take a look what are the common metrics in the regression task, and this is in the context of deterministic forecasting or the point forecast. So now in this notation, we're going to use E, the vector E, as the residual error that is calculated under the rule y hat minus y. So suppose your n is the number of samples in the test set or in the validation set or even the train set. For MSE is some square error and take the mean, all right, mean square error. For RMSE, you will put the square root. For MAE, you take the absolute value and then take the mean. For MBE, you take the sample mean, basically. So MAE and MBE, they are different by the by the absolute value. For MAE, it's always non-negative. For MBE, it could be a mixed sign. So under the definition of error as y hat minus y, This is up to you. I mean, there could be another choice as well. People may define it as a y minus y hat as well, but I prefer this choice because when I compute MBE, right? So if my MBE when I make an aggregate sample mean of all the error, if my MBE is positive, it means, and because my error is y hat minus y, so you can imply that your model is overestimate. And on the other hand, when your MBE is less than 0, right? So your model tend to be underestimate. So the choice of y hat minus y allows you, I mean, if you pick this choice, it allows you to interpret the sign of MBE in a meaningful sense. So these are typical the typical evaluation metric. And And of course, depends on the unit of the error. When you perform a forecasting, the error will have the same unit as y. So now in our context, um, ah, so if you perform the irradiance forecasting, the unit of your error would be watt per meter square. If you perform the solar power forecast, the unit would be in watt or kilowatt, right? And if you, this is solar or any renew, if you perform electrical load, your unit is still in watt or kilowatt. Okay. So when the variable, so when the error has a unit like this, um, of course, if you perform the study, perform the experiments, and then you evaluate among the models in your experiment setup, that is fine. You can compare which model perform best. But when you want to benchmark your models with the previous studies, so if you read the research paper and see that other people have developed this model, but they calculate based on their data sets collected somewhere that is not in your area, that is certainly not in your country, on your location. So there's going to be issues about the unit or the data range. Okay. Keep in mind that the solar irradiance, the range its range can vary over spatial area, over geography. So for example in the US, on the west side, the solar radiation tend to be high. It's supposed to be like a very clear sky over there, so the range of irradiance would be high. Okay. While in the tropical climate, like in Thailand, we have less. I mean, the data range is less. Is less. So that's why when you my only point is that now we talk about all of these metrics that can be normalized by removing the effect of the data magnitude. So we're going to use the term NRMSE, like we have N as normalized. So it's given by whatever metric you use divided by the normalization factor R. Okay. And then like make it percent. Normalized MAE, normalized MBE. And the choice of the normalization factor could be varied. There are many choices proposed in the literature. For example, in the context of solar power, renewable energy forecasting, the R can be the average of Y. Mhm. And remember, in the normalization factor, um, uh, I mean, it should be a single factor that can be obtained from a data set. I mean, this normalization factor is data dependent. In the context of solar irradiance, the average Y that refer to irradiance and the solar power should be average over the daytime only. Okay. And people also use another choice. This is data range, Y max minus Y min. Okay. And people may implement these things differently as well. In my opinion, suppose you have the data that are scattered like this. It might be the case that you have such a, I mean, if you haven't taken care of the data very well, it might be possible that your data has a lot of outliers. Okay. And if you didn't get rid of these outliers, it's going to make your Y max extremely high, right? When your Y max is extremely high, um, or the Y mean extremely low, is too low, too realistically low, it makes your R too big. All right. So that's unrealistic. It doesn't explain the majority of the data. So when your normalization factor is too big, what happened? I mean, you use normalization factor as a divider. It makes your performance metric too low and becomes too optimistic. And that's not fair in the performance evaluation when you benchmark with other case studies or another analysis. So for the data range choice, uh, there is uh, another solution, alternative choice as well. For example, you may take a look at the data histogram. Suppose this is a histogram of your Y, right? And then instead of picking the max minus min, you can pick a high percentile. Like for example, uh, at 95 percentile and at 5 percentile, and uh, use this range instead. Okay, uh, so maybe you pick the quantile at 0.95, and for Y mean you pick the quantile at 0.5, things like this. Okay, so that's why that's so if the data has a long tail, so you don't pick the maximum one. For solar power, sometimes people use the install capacity as R. Mhm. This one is common as well, but it has some practical issue as well. For example, For example, suppose your solar power, the measurements. Okay. Now, first, maybe at you have installed it at 2020 in 2020, and the power peak, the rated power is around 10 kilowatt, for example, and you get the measurement value around at the rated power. However, like many years pass by, suppose we're at 2030, and by then your solar panel become degraded. So this is at 10 kilowatt, but the measurement power that you obtain right now is less by a factor of half. It now becomes 5 kilowatt, right? So it means that when you perform the forecasting based on it all based, I mean, if you perform the forecasting for the solar panel or the solar farm that have been used for a very long time, right? So you didn't get the power as much as before. And then so the range of the error would be smaller than the error uh, when you first use the solar panel, which means if you normalize the data, the error by the install capacity, again, your R is going to be too big because you're going to use R as 10 kilowatt, right? But it's going to be too big for the behavior of your data set as of now. And then when the R is too big, your performance metric becomes too low, too optimistically low. And that's again, that's not fair. That's not an appropriate evaluation for reporting the model. Mhm. Um, I have some interesting notes that usually when we have analysis from linear algebra that when you compute the one norm, the two norm, there's going to be a principle that say by equivalence of norm. Okay, and that allows you to make a relationship between two norms, so you can find by equivalence of norm. So you will be able to find some constant M1 and M2. And then you can develop a bound between any pair of norm. That's what we mean by equivalence of norm. You can look up this result from the internet, or you can prove it by yourself. All right, phi M1 and phi M1 and M2. Okay. Mhm. So usually I leave it as an exercise, but now I would like to state the results that because MAE, right, is 1 over n sum of absolute value. So it is more like 1 over n, the one norm of E. Okay. On the other hand, for MSE, this is 2 norm square over n, right? For RMSE, so it's 2 norm divided by square root of n. Okay, so if we present all these performance metrics with the norm notation, and now you apply the principle of equivalence of norm, we can show that we can always have these inequalities. The MAE is always less than RMSE. So that can be a certificate uh, for your coding check as well. If the code is correct, it should follow this. Okay. On the other hand, the MAE has a lower bound as RMSE divided by square root of n. Mhm. So for a moderate data set, when n is not that big, okay, this lower bound can be a useful bound for MAE. So please verify this, okay, as an exercise. We have some guideline for making an evaluation in solar forecasting context. Because the analysis of performing the usually the curve of solar power should be something like this. Okay, so it's going to be 0 at night, right? And it's some non-negative value on the daytime, right? And when you perform the forecast, of course, at the nighttime is not relevant because everything is 0. So we take a look and we focus more on the daytime. So when you make when you make a prediction, right? Suppose uh your red line is the prediction. You can see that obviously if I now I'm going to plot another graph. Okay. So this is my y is my red one is y hat. My mint color is the actual y. So when I plot the error, what would I have? So I'm going to have some error, maybe plus and minus, but on the nighttime, I can get the zero error very easily because most of the time you can make a prediction that at the nighttime y hat is zero, right? So um, so that's why your error looks like this. It also implies to us that we should make an analysis of the error only the daytime, okay? Because half of the data is at nighttime, and those half data are zero error, okay? So uh, remember that when you have the error as the, I can draw the I can draw the error vector as the green line, right? So your error vector. And if you collect the error vector from data over a period, of course, this gonna be half of them would be daytime, half of them would be nighttime. Okay, and for the daytime, the values of the error vary, depends on your forecasting performance. But at the nighttime, most of the zero could be zero. So sorry, most of the error could be zero easily. So that means when you compute all of these MAE, which is 1 over n, for example, all right, when half of the error is zero, all right. So if you calculate MAE by using all data, it average out, half of them is average based on zero. So your MAE is going to be is going to be lower than using only the daytime in computing MAE. Okay. I have a note here that as well. I want you to verify it. If you include the nighttime data, it will overly estimate the MAE that is smaller by a factor of one half because half of the data is zero from the nighttime. And on the other hand, for RMSE, RMSE is square root, right? EI square. So, so if you include the nighttime in the study and evaluate RMSE, your RMSE is going to be too low by a factor of 1 over square root 2, which is 0.707. So So, like knowing this mathematical result, it is recommended and it becomes a common guideline that when you evaluate the error, you do it only on the daytime. Mhm. So the prediction error, as I mentioned before, is calculated based on the formula y hat minus y. So that the positive E indicates overestimation and the negative E indicates the underestimation. Mhm. For this, these are the nodes that I mentioned earlier. If you use the normalization factor R as the average of I, we only consider the daytime. So use the average over the daytime. Mhm. And otherwise, R is going to be too low and makes your performance metrics too high. Okay. Um, when you use a range, it may be overly large value if y has outliers. So you can use the R as the range from the percentile of 95 minus the percentile of 5. Mhm. Okay. Hmm. Here's what I mean. Okay, so this is my irradiance plot, all right, and this is a histogram of solar irradiance. Okay, you will see that there is one data, there is one outlier. Okay, there is one outlier that almost hit 1400. So when you plot the histogram, these become like a separate tail here. Okay. So when you use y max minus y min, the range is too high as a normalization factor. And when I follow the range that come from the quantile of 0.5 and at the quantile of 95, the range is smaller and it still guarantee the majority of the data, which is these portion guarantee to cover 90% of the data. Okay. Um, Another guideline when you perform the evaluation is actually going back to the step where you split the data set. I would like to go back to this slide when I mentioned in the previous video that okay. So we come back here. When you perform a solar forecasting, we follow this flow chart, all right? And the beginning is that to prepare a data set, and then you have to split the train, the validation, and the test. So there are some guidelines that you use and sufficient data for training because usually the model require uh, many numbers, a high number of sample size. Um, for validation and test, you can use less. But one thing that you need to make sure is that the distribution of the data that that uh, that hidden in each of those data sets should align. All right. Okay. Now let me go back. Where is it? Hmm? Mm-hmm. Eh, where is it? Ah, no, this slide. Okay. This is what we mean. So when I split the training set, the validation set, and the test set, you can see that the histogram of my data, which is solar irradiance, tend to be very similar. Um, this splitting, I didn't split based on the time ordering. I did split like, okay, the first half of the year is train, the second half of the year is test. No, I didn't use that because one issue is that now the climate has been very unpredictable. So if you have a data from a year, from a span of 1 year, right? So it could be possible that suppose this is Jan is in December. For example, in Thailand, the rainy season, I mean, according to our conventional season is that the rainy season start from July till September. But because of the climate issues, it's not follow this seasonal pattern anymore. Sometimes, sometimes you have rain in the beginning of the year in March. We have seen it before. Um, so that's why, according to this experiment, we just shuffle the days, like each day in the data set, we shuffle them according to the sky condition and make sure that each of the data set contains the same amount of uh, clear sky day, partially cloudy day, and the cloudy day. All right. So of course you can arrange the data according to that way, and that's gonna make the comparison, the benchmarking in each training set uh, uh, provide you a very meaningful results. For example, I mean, what was going to be an issue with you didn't shuffle the data in this way? For example, I can like make explain an example that okay, what if now, now I'm gonna make the plot again. So what suppose suppose this is your data set, right? Mm-hmm. Ah, let's say you use hold down method. You split the data set like this. Okay. So the first one you use it for train. Okay. Um, and the the second half is that you use it for test. Okay, my point here is that, okay, on your training set, you have a mix of a cloudy day with a few of the clear sky days. But on the test set, your model is trained on, sorry, on the test set, the data contains only the clear sky day. So the clear sky day are considered to be easy data, while the cloudy day, where there's a lot of fluctuation in the irradiance, are considered to be uh, a hard data. So that means that when you have the test data on these days, it tends to give you a low performance metric. All right. But then you will mistakenly understand that your model perform very well, right? But that's because you create a bias in the data splitting. Okay. Um, and one note is that the data in the training set should um should consist of the data from various conditions, from both clear sky and cloudy conditions, because you want to learn all kind of patterns of solar irradiance in your model. Mhm. um hmm, okay, now I would like to explain a little bit about a common way, a standard protocol when you report the performance of a forecasting model in a renewable energy context. First, because the solar power magnitude varies over day. Okay, according to the irradiance graph, right? It is less value in the early morning and afternoon, and it is at high magnitude during the day. So that's why when you compute the error, first you represent the metric, the performance metrics, based on each time of the day. So at 7 until 16. And then you can take a look at each metrics. Okay. In this graph, for example, first of all, if you look at the MBE, which is just the average of the error, you see this peak, right? The green one, sorry, the blue one from a certain model. This is WAF. This is a kind of numerical prediction, numerical weather prediction model. So it's a it's a model that atmospheric forecasting center has have been using to give you the weather forecast information. So it's considered to be a physical model. And now you see that you can say that because the MAE is positive, right? So this model tends to be overestimate. Mhm. And you see some negative values by this model. So this is a model that we developed in uh, in 2018. So it is a common filter. It is a linear regression model, but the regression coefficients can be adaptive using the concept of common filter. So now you can read that the MBE is negative, so the model tends to be underestimate. And then you compare the graph, you can compare the value among the methods. Okay. Hmm. Next, remember when we define the problem statement, we have to specify the horizon, horizon as h, right? And the resolution in order of minutes. Okay. Suppose um in this example, ah, suppose in my application, in this problem, I say that my resolution is 30. Okay. and my horizon is 4 hours. Okay, so I'm going to forecast 4 hours, and the resolution is 30 minutes. Okay. Uh, Now, how many multi-steps forecast should I provide? 8 values, right? Because for 1 hour, it has 2 values. So 2 times 8 times 2 is 8. So my my horizon, sorry, the number of the point forecast that I provide is 8, right? So that's why um the so there's gonna be 8 steps, right? And sometimes, a lot of time, people use the number of step you have to provide a forecast as the number of lead time. Okay, so the second way of looking at the performance metric is to calculate the error according to the lead time. Okay, so in this plot, your y hat t plus 1, the first lead time, or the first step, is going to be at 30 minutes, right? And you're going to have y hat t plus 2, y hat t plus 3, dot, 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 y hat t plus 8, right? And y hat t plus 8 refers to the lead time of 2 to 40 minutes. And so this is 4 hours. And when you compute the performance metric in this way, it gives you the sense that when you look further in the future, you already know that the quality of the forecast should be worse, right? Because the problem is more difficult, getting more difficult if you look far in the future. So that's why it's not surprising to see the performance metrics tend to increase as the lead time steps grows. But you want to see, I mean, you know that it's going to be an increasing trend, but I mean, the information that you should take from this, from your analysis is, uh I mean, how much higher as the number of steps grow. Okay. And the growth rate of your metric, of your error metric, from various methods are not the same. Can you see? So, for example, you can see that the red one, the random forest, all right, at these multi-step, the error tend to be the same, while the linear regression, the error tend to be significantly increasing for the first few multi-steps. Mhm. Okay. Um, the performance evaluation for for point forecast. Oh, sorry. These are the performance metric for the point forecast. We also have different ways of evaluating the performance of the probabilistic forecast as well. But I'm going to keep it in a separate lecture then. Okay, so so you can take a look at the handout, but we'll come back to this content again. Um, I would like to show some numerical examples, or should I cut the video? Oh, it's been 45 minutes. Um, so let me stop the video, and in the next video, I'll show you some numerical examples.